Hello everyone. We're going to be looking now at the action potential generation and propagation through my contractile cells. So the cells that are actually responsible for the physical contraction of the heart. We know that the action potential through these cells is going to be slower because we saw the pacemaker cells are specialized cells in order to pass on this electrical impulse really fast. But this goes through, the message passes through my contractile cells, but more slowly than it does in pacemaker cells. But how does that happen? So I've used the same graph as I did in pacemaker cells. So I've got on my y-axis, that is my voltage of the cells. So it is in millivolts, and my x-axis is in time. So it's going to be in milliseconds. And as a reference, I've put on our main actors in this process, which is my potassium, down at minus 92 millivolts. So that's what it would happen if it was only potassium going out in and out of the cell. Sodium plus 67 millivolt. Same again, if it was only sodium going in and out of the cell and there was the other ions weren't involved, that's where would sodium want it to be. And then finally calcium at plus 123 millivolts. That's what would happen if it was only calcium going in and out of the cell. At the bottom, you can see a representation of my contractile cell. And the two structures there on the left of the cell, they represent gap junctions. These gap junctions are literally two holes, two channels that are always open in between contractile cells. So what does that mean? That means that here then, I would probably have another cell, and what goes through these gap junctions, these are the leftover ions from a previous repolarization. So what we would have here going through, you would have all sorts of leftover sodium, for example, or you would have some leftover calcium. Here we go. Then we'll go through the cell into my cell through these gap junctions, and it's going to just trickle in. The initial resting potential of the membrane of a contractile cell is at about minus 90. So I'm just going to try to put it here. Here we go. Minus 90 millivolts. That shows you how much potassium really is involved in this. Yeah, so it's very close to that minus 92 where potassium really wanted to be. So that is my resting potential for my my contractile cells. Now, what do you think is going to happen now that we've got this calcium and sodium trickling in? And naturally, with an influx of these positive charges, a slow influx of these positive charges, my action potential is actually going to start going up, but not rapidly. Like here we go, just slowly it's going to start going up. And it's going to start going up to about minus 70 millivolts. Okay, and that's my minus 70 millivolts. Just like we've seen previously, this minus 70 millivolt, it's called a threshold. Here we go. And this threshold of minus 70 millivolt, what does it do? This is the threshold for some sodium voltage gated channel to open up. So we're just gonna write it here at minus 70 millivolt, my sodium voltage gated channels. Open. Now, as you'll remember from our previous lecture, because there is so much more sodium outside the cell than it is inside the cell, the rate of diffusion of the sodium ions into the cell will be very rapid. So there's loads of sodium outside, very little inside. This is going to increase my rate of diffusion, and this means that I'm going to have my sodium, pouring inside my cell. Like there's going to be loads coming in really rapidly. What does that mean to my action potential here? That after reach minus 70 and all my sodium channels opening up, this will happen. It's going to get a very, very rapid depolarization. Just like that. And it's going to reach approximately plus 20 millivolts right there. Just going to get our minus 20 millivolts right there. 20 millivolts, it is going to be another threshold for something different. So firstly, the first thing that happens at 20 millivolts is that my sodium channels will close. My voltage gated sodium channels will close. Close. There you go. But at the same time, something else is here that is happening. My potassium voltage gated channels will open up instead. So what's going to happen when some potassium channels, so we're just going to put it here because we have plus 20 millivolt potassium. So what's going to happen when potassium channels open up? Well, once again, because of the concentration gradients, we know that is loads of potassium. We managed that at the beginning, didn't we? That there's loads of potassium from inside the cell and just a little bit outside. So that's loads of potassium that will want to leave the cell quite rapidly. Here we go. Loads of potassium wants to get out of the cell because of its concentration gradient. So what's going to happen to my action potential then? I'm here at plus 20, my sodium channel, so this big influx of positive charges had stopped, and I had started instead and it started losing positive charges instead. So what's going to happen? It's going to start going down the way again. But it's not over yet. What is going to happen now? As soon as it reaches 5 millivolts, so just slightly positive here, as soon as we reach 5 millivolt, something else happens. Well, what happens at 5 millivolt is that we have triggered the opening of some calcium voltage gated ion. So talking about a plus 5 millivolts slightly. There is some calcium gated and let's not forget that I still got here my potassium one is still open. Yes, so I'm still losing positive charges through potassium, but now the difference is I've got loads of calcium coming in. That is loads of calcium coming in. So what's going to happen? See, if I've got positive charges leaving and positive charges entering the cell, what's going to happen to my action potential is going to form. They're going to balance out, aren't they? So what's going to happen here? I'm going to get some sort of plateau phase. Yeah? So the balance here is just these charges are going to balance out and form like a straight line here in my action potential. This is going to turn out to be very important because this is what we're going to call the refractory period of my cell. During this plateau, my cell cannot trigger another action potential. So it's almost like the resting phase of my cell. Now, the calcium voltage-gated ion channels in my contractile cells, they won't require particularly another type of voltage, a different voltage, in order to close up again. So what they do, when they hit plus 5 millivolt, they start opening up. And then as they open, then they close again. So they open and close. So that is what happens when they hit this other threshold. So they open up, let loads of calcium in, and then they close again. So what's going to happen at that point? So once my calcium channels close up, when my calcium channels will start closing, here we go. What's going to happen? Well, I'm still going to have, so my sodium ones are closed, my calcium ones here are closed, and I'm still going to have potassium leaving my cell though, won't I? So here I'm just going to add close, right? Spontaneously. Here we go. So calcium channels close spontaneously, and my potassium still coming out. So what's going to happen to my action potential? Well, you will have guessed it. If I have no positive charges going in, but I'm losing loads of positive charges there, what's going to happen? This is going to start going down again, this way, until I reach, well, finally, my minus 90, that where my potassium channels will close up. So at minus 90 millivolt, potassium channels close. And what's going to happen now? Well, it's simply the cycle starts all over again, doesn't it? Because here I'm still going to keep on getting a trickling in of sodium and calcium, and then my that is going to get my action potential up very slowly until I reach minus 70. At minus 70, I've got my sodium channels open up that are going to start pouring in and get this very rapid depolarization here, and so on and so forth, and it will carry on this way. So just to conclude, I would like to just name a few of the phases in here. So this flat stage here, so I'm just going to extend it a little bit at the bottom here so it makes more clear. So this flat stage at the beginning here that precedes the rapid depolarization is called phase 4. Put in red actually. It's called phase 4. It's 4 there. Phase 4 here. This straight, almost straight line up, that's what we called phase 0. Okay, and that is where my rapid depolarization. So the depolarization on my pacemaker cells is quick, but it is slower than in my contractile cells. Now, careful now, there's a confusion. The action potential travels faster in pacemaker cells, but the depolarization is slower in pacemaker cells. While in my contractile cells, my action potential travels more slowly, but the depolarization, the phase 0 of it, is actually much faster. So I've got phase 0, which is rapid depolarization. Then when I'm going to start having this outward flow of potassium here, that's what we call phase 1. There we go. Phase 2 is this plateau, yeah, which is my refractory period. Refractory period. Here we go. And during my refractory period is what we said, almost a resting phase of my cell, where another action potential cannot be generated at that point. That's why many antiarrhythmic drugs do target my refractory period by closing different channels here, by blocking different channels. And my phase 3, it's when my calcium channels, they get inactivated and my potassium keeps on pouring out of the cell. So this is my phase 3, which is called a repolarization, of course. And this is just a summary of your action potential in contractile cells.